Okay. Hello, Dr. Raj. This is my final presentation for my project. So I'm going to be talking about cochlear implants, and we're going to dive into the packaging and other qualities that make up this device, this biomedical device. So for starters, let's look at the function and biological system description. So the basic function of a cochlear implant is simply to stimulate the auditory nerves of the cochlea by bypassing the hair cell. So usually what happens is when someone suffers from sensory neural hearing loss, um, the sensory cells within the cochlea, which are the hair cells, stop working. They stop working. And those hair cells are the ones that would usually uh, be the ones that receive the signals or the sound of our environment. They would receive those signals and come and transmit them to the auditory neurons. So, and those auditory neurons would take them to the central nervous system, and that's how we hear, right? So the hair cells are the bridge between or better said, the hair cells are the ones that communicate all that information to the neurons so that we can hear. And what happens with somebody that has sensory neural hearing loss is that that stops working. So that's when the cochlear implant comes in, right? So it basically restores partial hearing by bypassing the hair cells. So it doesn't necessarily treat the hair cells, but rather it attempts to replace the function of the hair cells with electrodes, right? So the electrodes are the ones that, in this case, with the cochlear implant, sends out the electric signals. So usually what happens is that we can divide the cochlear implant in two parts. We have the external and the internal components. So we'll dive a little bit more into that later, but as far as where it's placed, so usually we would have the external component somewhere out here, which would be held by a magnet implanted on the inside too. And that implanted magnet holds the external part in place, right? Because the external part magnetizes to that internal one. Um, and the internal component of the cochlear implant would be surgically placed somewhere inside the same area where the external part would be, right? Because the magnets need to align, right, in order for the device to be held in place. Um, the interface with the body. So we have two interfaces. So we have the transmitter coil from the external component to the receiving coil of the internal component. And that's also why the magnet is there in place. This will also play a little bit of a role into how the device is charged. Okay, so we'll look into that a bit later. But then we also have the electrode array with the cochlea, right? So as I said, the electrode array is trying to replace the function of the sensory cells by sending the electrical signals to the auditory nerve. So by doing that, it also interacts with the cochlea, right? Because those electrodes are in the cochlea, right? So a little bit as to how it provides the intended function. So if we go ahead and actually here you can see the internal components and the external components. This is the electrode array flowing into the spiral form of the cochlea. We see the external component, which is the black, and then the internal, which looks it has white and gray, right? So they're aligned, right? So they're basically in the same spot. But that's essentially how you can see where everything is placed. Now, with the system architecture, this will tell us a little bit more about exactly how the system does work. So we can divide it into different parts. So we have the microphone, which is the aspect of the cochlear implant that takes care of picking up um, sound, right, and sound of the environment and convert it into a digital signal, right? It converts it into a digital signal through the speech processor, right? So in the external components, there is a encoder. It's an encoder in the speech processor aspect of the external components. There is an encoder, and that encoder well, encodes the signals into digital, right? And then through the transmitter coil, that signal is sent, the receiver coil picks it up, and then the implanted receiver, right? Because there is a part in the internal unit called the implanted receiver, has a decoder, and that decoder decodes the signal sent by the through the speech processor, and it converts it into electrical signals, right, that the electrode can pick up and properly send, right? So when the signals, when the acoustic signals or the sound from the environment are picked up and digitized, right, they are um, sent through an RF frequency link, right? So the way it's transmitted is that they're also turned into radio frequency. They turn into radio frequency, and that's how the receiver coil is able to receive it and decode it, and then send it out to the electrodes as electrical signals. Okay. Then how is power delivered? So um, power is delivered through inductive telemetry, right? So, but how it usually works is that the external part has a battery pack, right? It has a battery pack, and that's what charges the outer pack, right? Um, the outer components. And through inductive telemetry, right, the power of the outer components is able to charge the inner components, right? And that's achieved through inductive power and data telemetry, right? And as we can see here, we have a graph right next to us, right, with three different cochlear implants that were in the market. So we have the Nucleus Freedom, the Clarison Hires 90K, and the Metal Maestro. So in here, we're actually able to see and learn a little bit more about the electrical system description of some cochlear implants out in the market. So, for example, we can look at the input dynamic range, right? Which for the Nucleus Freedom is 75 decibels, 20 to 80 decibels in the Clarison Hires 90K, and 75 decibels again for the Metal Maestro. So the input dynamic range is what helps seeing how clean different sounds are picked up, right? So sometimes if you have a low input dynamic range, some cochlear implants make really loud noises. They become muddy, right? And really soft noises are not picked up at all. So increasing that input dynamic range allows it to pick up those sounds clearer, right? And this is actually, in a way, part of the innovations of the cochlear implant that we're seeing nowadays. I don't really talk much about it in my key innovation section, but I do think it's worth mentioning that companies nowadays are striving to increase and improve the input dynamic range so that there is a better pickup, uh, a better way for sound to be picked up by the cochlear implant. Additionally, we also looked at the frequency ranges for these three. 100 to 8,000 hertz by the Nucleus Freedom, 150 to 8,000 hertz by the Clarison Hires 90K, and 70 to 8,500 hertz from the Metal Maestro. So the Metal Maestro can pick up the lowest frequency sounds and the highest frequency sounds out of all these three. Um, so in that sense, it is the best one. Um, but then as far as the batteries, right, we see that they come in different forms. Nucleus and Freedom and Metal Maestro both last 3 to 5 days, right? And then the Clarison Hires 90K is only 14 to 24 hours, right? So, and one of them uses air batteries. Two of them uses air batteries, right? So we usually what happens, especially in modern cochlear implants, is that the battery pack will be rechargeable, right? So it is meant for the pack to last you a long time, given that the cochlear implant is a daily use device, right? So we want the battery to be long. And this is why you see these like lengthy numbers, like 3 to 5 days, battery powered, right? The Clarion Hires 90K is on the lower end, probably not the best. 14 to 24 hours is not ideal for somebody that needs the device constantly, right? Um, and other interesting facts that we can also see through this chart is the number of electrodes on each one. So if you notice, the lower number of current sources, the more number of electrodes the more number of electrodes there are, right? So the nucleus freedom has one current source and there's 22 electrodes. The current range is also 0 to 1.75 milliamps. And on the other end of the spectrum, we have the metal maestro, right, which has only 12 electrodes, 24 current sources, and 0.0 to 1.2 milliamps. Okay, so this talks a little bit about the electrical system description of the cochlear implant. Now diving into key packaging attributes. So to the left, we have the metal maestro. You can see a little bit there about some of the sizes or the real life sizes of the device, right? So, it's not super big, but it's also not the smallest. It doesn't show it here, but the metal maestro 1250 does provide a range of different electrode sizes depending on the size of the cochlea of the patient, right? That's something to take into consideration. Not everyone's going to have the same size of the cochlea, right? Maybe younger people need a smaller size. Some people just have smaller sizes or larger sizes, so you need that different range, right? So at least as far as um number of electrodes placed, right? So as we could see here, we saw that it truly varies, right? It truly varies. The nucleus freedom has 22, the Clarion Hires 90K has 16, the Metal Maestro has 12, but it has been found that there can be up to 24. I think the Metal Maestro 1250 actually is the one with 24. And the signals picked up is about 50,704 pulses per second across 12 electrode channels, right? So this is a different device. We're talking about the Synchronic 2 cochlear implant. So with the Synchronic 2 cochlear implant, we have 50,704 pulses per second across 12 electrode channels. Other key packaging attributes to talk about is definitely the hermetic packaging, right? So as far as the internal unit is concerned, right, that's obviously interacting with a lot of the bodily fluids that we have inside, right? So how does that prevent the entering of moisture? Um, so according to a study done by Park and his colleagues in 2007, they were designing a simple cochlear design, cochlear implant design, and they used a lot of the information, a lot of the materials that we actually discussed in class. They had a titanium package, they had platinum feed-throughs, and that connected the electrode rays to the receiver chip. And they had a ceramic plate that to hold the feed-throughs in place, right? So this is very in line to what we've talked in class. And as far as the sealing goes, they use blazing and laser welding techniques to create that seal, and they only use silicon oxide to close those gaps between the feed-throughs and the ceramic plates to prevent any type of leakage, right? Okay, key innovations. So when talking about key innovations, and here we talk about two. So we're talking about miniaturization and material improvements of electrodes, right? So electrodes recently, right, or at least over the last years, they're oftentimes manually manufactured, and what's used are metallic wires, platinum tips, and silicon carriers, right? So these manually manufactured electrodes not only take long to do, they also end up being really bulky, right? They end up really bulky, and that limits a lot of its performance, right? Because uh, if something is bulky, you may not be able to access the innermost part of the cochlea, right? So the cochlea is divided into three parts, right? And that would be the most starter, the middle, and the scala tympani, right? So most of the issues with these electrodes that are manually manufactured comes with the scala tympani, which is the innermost part of the cochlea. So a lot of the times, these bulky electrodes do not reach there, right? They don't reach there, and they're not able to access the low frequency auditory neurons that are found there. And also through a study published by the International Conference of Engineering, Medicine, and Biology Society, you can also see that when they're manually manufactured, since they're bulky, right, they're also only reaching 20 neural stimulation sites compared to the 3,000 that they could reach, right? So it definitely limits the performance a lot. So an innovation for this is definitely the microfabrication of electrodes using a photolithographic approach and a silicon micromachining method, right? So next to us, we actually have a substrate and electrode manufacturing process similar to what we've seen in class, right? So they have the thermal silicon oxide on both sides with the patterned aluminum. Then they deposit the seed layer, right, of polyamide. They then have a titanium nitride, and aluminum deposition on top of the polyamide, right? And this is then patterned, right? So it's patterned using aluminum. Um, and they also add a little bit of a layer of titanium on top of the first aluminum pattern, if you notice. Then this is patterned using titanium nitride and titanium. Then there's a second layer, second seed deposition, right, of polyamide. Then there is a hard mask of aluminum. Oops, sorry. And then there's this sacrificial aluminum and hard mask removal, right? And then you're left with the electrode itself, right? And this is sort of the newer approach that we're seeing in the industry regarding electrodes, right? To not only improve the materials, right, but also use materials that allow microfabrication, right? So through the microfabrication process, you're able to reach maybe more neural stimulation sites, right? It's not as bulky. Now, it probably would be more costly, but this is the price to pay to get a better and more efficient electrode electrode array for the cochlea, right? You just have to. If you have a bulky one, then it's just not going to be as efficient. And finally, when talking about MRI resistance and safety, a lot of the issue comes from two parts, right? So it comes from the magnet in the internal unit and also the titanium package of the hermetic sealing, right? So as far as the magnet itself, right? It's a problem because it can become demagnetized and it can become even it can suffer a change in polarity, right? It could change a form in polarity through the strong magnetic pull, right? The magnetic field that is created by the MRI machine, right? So what a lot of people are doing nowadays is that with the commercial cochlear implants, it makes it easy for the magnet to be surgically removed. So that has been the approach that has been taken up as of late. And I couldn't really find much of an innovative solution to this issue. However, I was able to find a solution to the titanium package issue. So even though the magnet can be surgically removed, you're still left with metallic components inside of the internal unit, right? You cannot remove the whole device, the whole internal unit. So that internal unit that it's titanium made up of a titanium package causes a image artifact, right? So it distorts the image of the MRI that the MRI can produce due to the fact that it's a paramagnetic metal, right? So since it distorts that image, it prevents, patients or people using cochlear implants from getting clear results of stuff that they need, So whenever they need to go to the doctor and need to get an MRI, you don't want to have less of a chance of detecting maybe a tumor or anything like that, right? Just because of the image artifact that the titanium package creates. So, solution to this is the use of polymers, but not just any polymer, because most polymers do have a lot of moisture absorption. Um, and that makes them useless for hermetic packaging. So a different type of polymer uses the liquid crystal polymer, which is thin, flexible, it's mechanically stable and biocompatible. It also is really good for because it's a thermoplastic polymer, and it can be easily encapsulated using a thermal press process, right? So thermal press bonding process. And unlike most polymers, it also has really, really low moisture absorption and low permeability. And to the right, we see here to the left, also image A would be the typical internal unit with a titanium package, and the one on the right would be the internal unit that uses the liquid crystal polymer. This is my presentation for today for the cochlear implant. I hope you have a great rest of your day. Thank you.